Good morning, everybody. It's our pleasure to talk today to Professor Humberto Campins from at the University of Central Florida, and with Bruno Coelho, that works at the Telecommunications Institute here in Aveiro. Well, I prepared a few questions for you both. Since I suspect this is for students, the first one, the last one, will be to try to guide them or to give them some ideas about what it entails to come into the profession. So my first question to both of you is, first of all, coincidentally, both of you had an interest in galaxies. Okay, it was the subject of Bruno's thesis, and it was an early interest from Humberto, if I understood correctly. Currently, your main topics of research are completely different. So maybe it will be interesting for our students if you could tell us a little bit about your career paths and your key moments, and what made these changes that brought you both to where you are now. Maybe I'll start with Humberto.
I was a summer student at the Kitt Peak National Observatory in Tucson, Arizona. The summer before I started my PhD program at the University of Arizona. So I happened to get the two of them independently. So I moved to Tucson a few months earlier, and I was working in the summer at Kitt Peak. And at that time, my advisor had all these images of galaxies that he wanted analyzed. So I helped with the analysis of these images, and it was very interesting, and I thought it was fascinating. But I had also had a summer internship a year before at the observatory in Venezuela, in Mérida, and one of my mentors, Ignacio Ferrin, was interested in comets. So, and I said, well, they're both fuzzy, they're not point sources, and that's what, that was my connection. But I continued on to study comets, and my PhD thesis was in comets, and then I continued to study comets or objects that were in cometary orbits, but they behaved like asteroids. They didn't have a fuzzy atmosphere and a tail, and so we called them transition objects. And then that got me into studying more asteroids, and now I'm at the end of a project called OSIRIS-REx, which went to an asteroid, picked up a sample, and it's headed back to Earth in September of this year. And but then I'm part of a team that has proposed to go to a comet and pick up a sample and bring it back. So that's called CSER, and it's being headed by Cornell University, and I'm part of that team. If NASA gives us the funding, we will launch around 2029, 2030, and go to the nucleus of a comet and bring back a sample. So it's galaxies, comets, asteroids, back to comets.
Okay, so in my case, my passion, let's say, was always galaxies. I always wanted to study galaxies, especially those with AGNs, which have these supermassive black holes, and they release a huge amount of energy. But the practical reason is not only you have the job to do what you want, but you need to pay the bills. But you learn the skills that can be used in other fields, because in the end it's all about image processing techniques and these kind of things. So I started working on data for other people, and I did other things. I even work in radio astronomy, which is completely different from the optical astronomy. And this increased in me the interest for different fields, different areas. In the end, they all connect somehow, and that's very interesting because you get a broader image of the surroundings of the entire universe in the end. And now you have another reason to do. I'm working in space surveillance and tracking of space debris, and so objects, man-made objects that are orbiting our planet. And astronomers are complaining that they pass in front of the telescope, so you want to observe the universe, but you have all these objects passing and messing your images. And that's very interesting also to try to study these things as astronomer, how we can deal with this in image processing, for example, to keep the astronomical data, but at the same time, it's something that I never thought in the beginning of my career, which is I'm working on a practical thing for the society. It's not a theoretical thing. It's not just I want to know how this works. It's a problem in our society nowadays because we have all these things in orbit, and we need to keep tracking these objects to see if they are safe. So if our satellites are safe, and our lives depends on it. So it's very interesting.
If I may,
Yeah, sure.
I also ended up in a field where there's a practical aspect of it, which is there's two aspects of the practicality. One of them is that asteroids can be hazards, impact hazards to Earth. So if one is coming, we need to learn how to deflect it. The other thing is they can also be a place where you mine for material, so you extract resources like water, and then you use them for human activities in space. And so I, somewhat unsuspecting way, I ended up working in an area that also had a practical interest. Although my original interest is purely scientific.
Yeah. The same with me.
Yeah.
But listening to your answers, it reminded me of an old teacher that when last students were trying to get their PhDs, and she said, the topic doesn't matter if the question is interesting enough. So I think that's what drives persons into research. It's an interesting question.
Yeah. Yes, curiosity.
Yes,
Yeah.
that is true, and it's interesting because recently I've been hearing from there is a program in the United States called On Being, and they interview philosophers, poets, scientists, and they talk about what is most important is the questions, not necessarily the answer, because you may or may not find the answer, but the question motivates you and takes you into a path where you end up learning all these techniques, or you're learning about other fields, and those questions make you richer,
Yes.
even if you never find the answer. So I like that example that you gave. If the question is interesting enough.
It keeps motivating.
And we have to also acknowledge that we are hugely privileged as scientists, that when we find a field that we like and we pursue the research and something unexpected comes up, it could be that that line of research is even more interesting than the original one. And that's the beauty of basic research. When you do applied research, you're going to improve this type of liquid to put into some kind of a process that is going to make the chemical plant work better, right? That you're doing applied research. But for us, it's like, okay, I was interested in comets, but look at this asteroid. It's, what's wrong or what's interesting? And you go that way, and it opens up a new field. So it's, I have to remind myself of how fortunate I am that I've been able to pursue what I like best, which is astronomy.
Yeah, sure. You mentioned the Osiris-Rex mission that will bring the sample in September this year. What were the team expectations for the sample? What were you expect to get from that?
It's the main driver of the science was to bring back organic molecules that were suspected to be in this type of asteroid and are believed to be the molecules that existed on Earth before life formed. So let me step back for a second. So the study of the organic molecules on that asteroid was the main scientific driver of the mission, and it still is, right?
Okay.
And it's interesting because I got invited onto the team in January of 2010. And I had submitted to the journal Nature a paper on the detection of water ice and organic molecules on this asteroid called 24th Themis. In any case, so I go to my first meeting of the team in February, and they said, okay, we're in good shape. NASA likes our proposal. We are in the final three, so we're competing for this money. But one of their few comments where we could improve is that we're going to an asteroid to look for organic matter, yet organic matter has never been detected on an asteroid. Has been detected on meteorites, which we think come from those asteroids, but we never detected on the asteroid. So what if we don't find it when we get there? And I raised my hand and I said, there are two papers that are coming out in Nature. One is the one I'm leading, and the one is being led by the other colleague sitting over there. And we're independently reporting the detection of ice and organic molecules on this asteroid, taken at different times and different parts of the orbit and different rotations. So our papers complement each other very nicely, and it's rare that Nature will accept two papers on the same topic to come out at the same time. Anyway, so they said, okay, so can I have a copy of the paper? No. Why? Because Nature has sequestered this until April. And until the paper gets published. And they said, okay, could you, as soon as you are allowed, could you give us a copy of the paper? And that actually coincidentally made our proposal stronger. And they invited me because of my expertise, but they had no idea that I was publishing this, because it was secret until it gets published. And so it's one of those things that just it worked in our favor. Yeah.
Okay, and the Japanese mission that brought also a bit of an asteroid, were they looking for the same stuff?
Essentially, yes, but I was not part of the. I mean, I worked a lot with the Japanese. I still
don't
do.
The results are out yet.
But they're starting to publish their results.
Okay.
But their motivation was to go to a primitive asteroid and to study its composition, and it's not clear if their main motivation was organics. Ours was, and let me explain why organics are so important. And it's because the origin of life we still don't understand. We don't understand that step from a complex organic molecule to the first living cell. And there's a couple ways to go after it. Study fossils that are more and more primitive to see if you can understand the first cells, which is hard because those are older and older, right? Or study more and more complex organic molecules and see how that step to the first living cell is. But the inventory of organic molecules that existed before life formed is gone. It's erased by life. The moment that life formed on Earth, it started transforming its environment, and it erased all records of what came before it. And the only records of what came before life on Earth is in asteroids, which have not changed very much because they're not big. They're not subject to the same processes of erosion and volcanic activity and all of that. And so in asteroids, we have the organic molecules that existed on Earth before life formed. And we believe they came from asteroids because the Earth formed very hot. If it had any organic molecules, they were burnt. And eventually, when it cools and you get a solid surface, then that surface is inert because all the organic molecules are gone. It impacts with asteroids and comets that deliver the organic molecules back to Earth. And that's how we believe life may have formed. And not just on Earth, but on Mars, on the moons of Jupiter, somewhere else, if we ever find life there, we would like to understand how it formed. And by studying this inventory of organic molecules in an asteroid, we are helping to understand the origin of life here on Earth and elsewhere, if there is life elsewhere.
Yeah.
I am sorry I didn't allow you to discuss much of your perspective.
It's very interesting.
No, but I'd like to hear from you. We had two main justifications. One practical one, which was that this asteroid was a potentially hazardous asteroid, and the other one was the scientific one.
Okay. In your current research, which is surveillance, so you are in the first line. Everything that goes up needs to cross this huge amount of debris that is increasing rapidly. So can you tell us a little bit of what are we doing in Portugal in the field, and how this ties up with the international efforts that trying to understand?
So there is a program, a European Commission program, which is called European Union Space Surveillance and Tracking. And Portugal is one of the members. The program is now being extended to several other countries in Europe. And in the case of Portugal, the program is led by the Ministry of Defense, and we are collaborating with them. So we have the technical skills and expertise to helping them in the setting up the sensors that will monitor the Earth. The idea here, and that's why it's a several country effort, is you want to have the entire Earth covered with sensors in different places of Earth, because you have the objects orbiting Earth and you need to track. What we want is to know exactly the path they are going around Earth. And we have more and more objects nowadays with all these mega constellations that are going into space, and accidents can happen. So we need to track all of these objects, because we have a problem. When you have private companies and different countries operating in space, sometimes they don't talk to each other. They don't say, I'm turning my object to that direction, so you move your object to the other one. They don't talk. So we need to monitor, and we provide the alerts, and then they deviate their objects to wherever they want, and that's it. So you need to monitor all these things. And you have two security issues here, because these objects can fall into Earth. Usually they burn entering the atmosphere, but sometimes they don't. It happened in the past. And the other thing is more and more our practical lives. So in our daily basis we use, and we are dependent on services that depend on satellites that are in orbit. So we need to keep those satellites safe. So otherwise we have a problem. You have internet, communications, navigation, everything is depending on satellites nowadays, so we need to keep them safe.
When you say tracking, can you give us an idea of how many of these objects?
Well,
or debris?
We have the catalogs we have. We are talking about hundreds of thousands of objects that are being monitored. But we have a problem, because we are just able to monitor objects at the size of 10 centimeters, sometimes, depending on the material, a little bit less than this. But the majority of them, they are very small, and they can provoke huge damage, because in space there we don't have atmosphere, so the speeds that they can reach are very high, and even a very few millimeters particle hitting a spacecraft at that speed, it's catastrophic. So the problem is how to detect these small things, and it's very hard, very complicated, and we need to push the technology and the efforts in that direction.
I have a question.
Sure.
The size distribution tends to be, you have relatively few large objects and more of the small ones.
Yes.
Because of the collisional erosion produces more small ones.
Exactly.
So the big problem is the small ones that you cannot track.
Exactly.
Yeah, right? Yeah.
And you cannot clean.
No. Well, nowadays the satellites that are being launched to lower orbits, they need to have just enough fuel to deorbit in the end of their mission. So usually they made the satellite enter the atmosphere to burn in the atmosphere, and they keep the space safe, and well the space can be used in the future, right? But for example, in geo orbits it's not feasible, because it's too far away. You need too much fuel to burn it. So what they do is they deviate the satellite from the geo belt, so the place where usually you put the satellite to, usually for communications, can be used in the future. You deviate that satellite that you have now in the end of life, to higher orbit. But they remain there. So for example, when you want to launch your mission towards an asteroid or something like that, you need to avoid those objects too, for example. And collisions can happen even in that region also.
The terminology is GEO for geostationary and LEO for low Earth orbit.
Exact.
Okay.
Exactly.
And so I understand that the most crowded area is the low Earth orbit.
Exactly, because it's cheaper to put objects in lower Earth orbit. You need less fuel. So that's why you have the majority of satellites in lower Earth orbit.
And I just thought of something that, and I'm sorry, you're the moderator, but I just thought of
You
another
are
question.
doing my job much easier.
And we have a similar problem with near-Earth asteroids. The bigger ones are easier to catalog because they're big, they're bright. We can detect them. For example, we've detected more than 90% of the ones that could cause global devastation if they were to hit Earth. And right now, none of them are threatening Earth. But as you go to smaller objects, they are harder to detect, and there are more of them. So we could be surprised by something that is large enough to make it through the atmosphere and hit a city, but they're too small for us to be able to detect with the techniques we have now. Now, they won't destroy the whole planet, but we wouldn't want Aveiro to be hit by one of those,
Yes,
right?
exactly.
So there are a couple of missions. One of them is being funded by NASA to put a telescope between Venus and Earth and to be looking out. Because when you're trying to look at objects that are inside of the Earth's orbit, you're looking into the sun. And that's very difficult. But if you move in and you're looking out, you can see many of the objects that come close to the Earth and reflect sunlight or are heated by the sunlight, and you pick them up in the infrared. But you're looking out, and it's much easier to do that. So that's called the Near-Earth Objects Surveyor, and it's being funded by NASA. And I understand the European Space Agency has a similar project.
Yes.
And so these are going to be complementary, and those will be able to go down to like 140 meters and detect something that could affect the city, and therefore catalog them and plan to either deflect them or do something to mitigate the impact.
Just very quickly, there is also an interesting thing. It's just not the size that is make these objects hard to detect. For example, I mentioned that the majority of satellites are launched to LEO orbits, which are very low Earth orbits, so close to Earth. And what happens is, the closer the object is, the same speed, traveling in a direction perpendicular to the line of sight, seems to be much faster, and that makes the observation really difficult. So it's extremely difficult to track objects in LEO orbits, because they are too close to us.
Right.
So here in IT, we are developing a LEO radar to measure the distance to these objects, to track and measure the distance, and we are developing also optical sensor to track and monitor these objects in LEO orbits, but this sensor needs to move very fast. The other problem is, when you move really fast, you have a very short period of time to take the measurement, and that makes even harder to get very good measurement in such a small period of time.
And on objects that are not very bright. Because
Exactly.
So yeah.
Is this what we are doing in the Pampilhosa da Serra
Exactly.
observatory?
Yes, we have a observatory at Pampilhosa da Serra in the dark sky area in Portugal. So we have a radar with a 9-meter dish that the whole system is being developed by our colleagues here at IT. And we have a surveillance telescope of the Ministry of Defense already operating there. But that's for MEO and GEO orbits. So the GEO orbits are the furthest of the satellites we have, and then the MEO is intermediate objects between the GEO and LEO. So that telescope is doing surveillance right now, sending data to the European Commission. And we are developing this sensor for LEO, which are actually 2 telescopes with large field of view, because the uncertainties of LEO orbits are very high due to the drag of the atmosphere. So sometimes from one passage to the other, the orbit may change a little bit, so you need to have a good margin to track the object. So we have large field of view telescopes. We have filters also to try to minimize the background, because the other thing is they just reflect light if they are illuminated by the sun. So if they are very close to the Earth, you have a very narrow window at sunset, at sunrise, and sometimes the sky is not dark enough, so it's very difficult to observe objects very close to the Earth.
It's interesting how many parallels there are between what you're doing and what we're interested in. Our objects are further away, but basically the challenges are similar. If they're too close to the sun, if they come too close to the Earth. And so, for example, in 2029, asteroid Apophis will be coming between the geostationary satellites and the surface of the Earth. We know it's not going to hit the Earth. We know its orbit very well. So Apophis is going to come real close to the Earth in 2029. And even though we're not worried about an impact, we want to continue to study it in case it becomes a threat in the future. And the OSIRIS-REx spacecraft that I've been involved with, it's going to drop the capsule in the Utah desert in September, and then go basically into a standby orbit until 2029. So when the asteroid comes real close to the Earth, it will match orbits and study it in detail. It's going to do a rendezvous, and actually it might even go into orbit around it. And going into orbit around a very low gravity object is difficult, and we did it around Bennu, but the object is even smaller. So when it comes real close, it's going to be basically within your field of view, and you will be able to study it and maybe even see our spacecraft come and rendezvous with it.
Yes.
But it is difficult because the closer they come, the faster their apparent motion is,
Exactly.
and
you need more sensors around the Earth to keep track of these objects,
right,
because you are observing a smaller portion of the sky because they are so close to you.
Yeah.
If you are doing the sun, you just need 3, like in 8-hour intervals. If you do this, it's because they move faster. But one thing that we keep discussing the things we don't know, and you mentioned that in 2029 the asteroid will be very near, will not collide. Is the majority of persons, I think they don't understand the precision that current predictions of dynamics of these objects attain.
Yeah.
So there are things we don't know, but it's fantastic. I work in history of astronomy, so for me it's really surprising that you can pinpoint in a few years' time where the asteroid will be.
Which is, I think it's remarkable, and I find it fascinating that we can do that, and we know that it is not going to hit Earth. There's not a chance, even though it's coming between the geostationary orbits and the surface. There's still a lot of space there, and the asteroid is small compared to that space. But I am amazed, for example, with the results of LIGO. That means even more precision. So LIGO is these observatories that detect gravitational waves. And Einstein predicted that would be possible, but he said practically it's going to be very difficult, if ever, done because the precision that we need. And the achievements of LIGO make our astronomical predictions seem like child's play compared with their precision.
Well, that's a fantastic idea by Michelson.
Yes.
The guy that invented the interferometer.
Yes.
Which is the first American scientist, I think, that won the Nobel Physics
I didn't know that.
Prize. Yes, and that is a game changer. It's a new instrument that allowed very, very precise measurements.
Yeah.
So LIGO doesn't impress me much. Because it's just a scaled up version of the same instrument.
Yeah,
but it's very clever. Technologically, it's very complicated.
And they have to take out all of these other sources of noise. And in our case, we have to take out, it's not noise, but we have to calculate all of these different influences on the orbit. For example, the asteroid is rotating and it's reflecting sunlight in one way, and it's re-emitting the heat that it gets from the sun in a different way. And that can change the orbit ever so slightly from a Keplerian, from a purely gravitational orbit, of being in orbit around the sun, and also the close encounter with the Earth. It's going to change its orbit because now you have two bodies affecting its path, but also the way in which it reflects sunlight and the way in which we emit sunlight, in the long term, that can change its orbit in a way that could either move it towards an impact with the Earth or away from an impact. So we need to continue monitoring all these little factors that change the orbit of a non-spherical, rough surface asteroid that comes close to the Earth and can come close to Mars or Venus, and all these things that are constantly changing, and we need a long-term monitoring of these objects.
Yeah, sure.
Yeah, and then it's interesting that our fields will overlap with and do overlap with objects like Apophis, and there are others that we discover and on short notice come that close to the Earth.
Yeah.
We discussed a little bit about the objects coming close to the Earth, and some might enter into the Earth atmosphere and even collide with the Earth. But may I ask you a broader question about what do you think is the future of space exploration? In the sense, it's just our continuous strive for more knowledge, or do you believe that we'll start to have economic interest in space, exploration of the asteroids, and even in future human colonies elsewhere in the solar system? How this will...
I would like to hear what he has to say first.
I think that, and as astronomer, of course, that the interest in space, it's there, and by curiosity and everything. And as much as we want and we would like to know about space and explore space, we need the economical interest to get the funds to do this research. And this economical interest in space is appearing. As scientists, we can take the ride and study and answer our questions, but unfortunately or fortunately, I don't know, I'm not the person to judge those kind of things, but that's the truth. You need the economical interest to do this, to push the things. Because I remember even to monitor asteroids, scientists, this may impact Earth, but how many people saw an asteroid impact Earth? And you ask for money to put a telescope observing the sky the entire night, and it was difficult to get the funds for this. Nowadays, you have telescopes around the world popping up because everybody wants to know where the satellites are. So it was the economical effort, the economical interest that allows us to have the telescopes. But the data is there. I can observe the satellites and I can observe the telescopes. So that's, things go together.
I agree. And to address your question, let me start actually from the broader perspective. Is we are explorers, and I think that as scientists we are interested in studying nature, but humans have this urge to explore, and maybe that's what got us out of Africa and into the rest of the continents as Homo sapiens. Mm-hmm. It's that we wanted to know what was over the hill, and it's possible that that's one of that urge from early humans, which is still in our genes. It still is driving our exploration needs. So human exploration of the solar system will likely continue because of that urge. It is difficult. For example, getting to the surface of Mars is not simple. You are likely to make a stop in the moons of Mars where we will have sent robots to process the surface of both of the moons of Mars, which are captured asteroids, and generate fuel for then the spacecraft to go down to the surface and come back up. And on the surface of Mars, you're likely to find the raw materials to produce fuel, water, essentially break it into hydrogen and oxygen, and then you have fuel to come back. But it is much easier to go to the moons of Mars and come back than to go to the surface of Mars. So I predict that we're going to go into orbit around Mars as humans first, and eventually onto the surface of Mars. So that is the exploration side. The financial side is, in the case of asteroids, the moment that you can produce water in space cheaper than it takes to launch it into space, then you have the fuel to service all of the Earth orbiting satellites that need that fuel. And right now they're getting launched with the fuel, and SpaceX and other launching systems are charging them per kilo of putting this thing into space. It's not feasible right now, but eventually in the next 10 or 20 years, we will be able to mine asteroids, produce water, break it into hydrogen and oxygen, and sell that hydrogen and oxygen as fuel to the Earth orbiting satellites cheaper than launching it. The moment that that happens, you have a self-sustaining space economy where you have the source of the fuel in asteroids, you mine them, and then you sell them to these Earth orbiting satellites for communications, for Earth observations and weather, for military purposes, that would prefer to buy it from you because you charge them half of what SpaceX is charging to put it into orbit. So there will be a self-sustaining space economy, and there will be all these financial interest in going to asteroids and finding which ones are going to have the best material to process and produce the fuel. And therefore we're going to have, as scientists, a lot of little spacecraft going to all these asteroids and studying them in detail that we wouldn't have had if it were just science. And so the combination of what you were saying, the economic incentive, the scientific curiosity, and I think very important, the spirit of exploration. As humans, we want to explore. We want to go to the next frontier, right?
Yeah.
And it used to be the New World and the Americas and the Wild West, and now it's space. And
I think there are only two. It's space and the bottom of the oceans.
and inner space.
The only two that are...
Yeah, and inner space. I mean, for example, in physics, the particle physics, and trying to understand what's in the fundamental elements that make up our universe, right?
Sure.
And anyway.
And I think we are, in the end of our time. But I would just ask you, for if there are students watching, what do both of you think are the required skills that they should learn? Obviously, they need a good foundation in physics and astronomy. But what other skills would you think they should learn to be future researchers in your field?
You have to learn how to work in a group. It's more and more, all of our endeavors are so complex that you have to work as a team. And so you need to understand the mathematics, you need to understand the physics, you need to understand all of these skills that individually you can contribute, but you also have to learn how to work as a team. I'll give you an example. When I joined OSIRIS-REx, we were just finalizing the design and the needs of each instrument. So we had cameras, we had spectrographs, and scientists wanted all the cameras and all the spectrographs to work all the time with the highest possible resolution and send all of the data to Earth, right? And the engineer said, that will cost you another $1 billion. And we said, oh, all right. I'm simplifying this, but I learned how to speak engineering. I didn't know how to speak engineering. I was a scientist and I wanted everything with the highest resolution, all the data, all at once, right? And the engineer said, you're going to have to compromise here somewhere. And so if you design for all possible options, your instrument is going to be hugely expensive. You need to narrow down what it is that you want, what is the essential data that you're going to need to carry out your minimum mission. And if you have extra resources, then you can be a little bit more aggressive or ambitious with your project. And to me, that was a huge learning and very useful experience, which was to talk to engineers. And then, of course, the engineers want to design the best possible instrument, but they don't know about what it is that the science wants. So it's important to have that interaction.
Well, I would say, of course, you have the logical skills that you need to have, mathematics, computer science nowadays, and all these kind of things. But you need to be stubborn, you need to persevere, you need to really like this, because sometimes you don't have the answers that you are searching for. Sometimes things doesn't work because we are pushing the limits of the knowledge. So no one ahead of us sometimes did what we are trying to do. So we don't have no one to ask how I do this. And sometimes it's not easy. It doesn't work at the first time. It doesn't work at the second time. So you need to be open-minded.
Okay. Well, thank you very much.
Thank you.
It's been a pleasure.
Yeah.